Hello, this is Mr. Stansbury. I'm going to take you through the notes on exponential functions. At the end of this, you should be able to say, I can identify exponential functions, and I can determine the decay or growth factor of an exponential function. Okay, so first things first. For exponential growth and decay model. So growth is when things get bigger, decay is when things get smaller. We'll take a population model, for example. Population at time n will be 200, and then we got 1.05 to the end. So what this 200 stands for is that's our initial population. 1.05 is the growth rate. We'll talk about that more here in a second. And then n is the time. Okay, so initial value 200, growth rate 1.05, and number of growth or decay periods. Okay. This here is, so this one is a exponential growth, and then this one is decay. The way you can tell the difference between the two is that growth is above 1. So growth, we'll just say x is greater than 1. Decay models, x is less than 1. So notice how this 0.95 is less than 1. So this is decay, and this is growth. Okay. Now let's see. For both, 200 is the original population. Okay, so if you're to plug in 0 for n, that anything to the 0 power turns into 1, so we just get 200. Okay, and then the first equation, 1.05, means that the population is growing by 5%. And here's the easiest way to figure out what the actual percent is take what the actual growth or decay rate is take your original 1.05, okay, and you can think of that as, say, 105%, because you move the decimal over twice to turn it into a percent, so that's 105%. Subtract 100% from that, because you're always going to have the initial amount plus, that's the 100%, and then whatever extra amount you have on that is your growth rate. So we always subtract 100% from that, and we take 105 minus 100, and that gives us 5%, and there's our growth by 5%. Okay? On the decay model, second equation, 0.95 means the population is decreasing or decaying by 5%. And you do the exact same thing with that. We take, say, 0.95, move the decimal over twice, and we get 95%. Okay, we're still always going to subtract 100%, regardless of if it's growth or decay. So we subtract 100% from 95%, and we get negative 5%. So the negative means decay, and it's decaying by 5%. So it's decreasing by 5%. Okay, we're going to take a look at some real-world examples here. Well, real-ish world examples here. Penelope's been tracking a population of Emperor Tamarin near her home. The population is given by P equals 42 times 1.06 to the n, where n is the number of years after the first population was recorded. First off, is this growth or decay? Since this number here is greater than 1, that means it is growth. Okay, and then what's the growth or decay rate? This is the big thing that we're going over on this section here, is we take 1.06, move the decimal over twice, 106%, subtract 100 from that, and we get 6%. 6% is the growth rate. So every population, every year, this population of Tamarin is going to go up by 6%. Okay? Find the original population. So original population, that's when time equals 0. So this n up here, that's the number of years. So that's when that equals 0. So officially that's going to be 42. Population is going to equal 42 times 1.06 to the time would then be 0. Anything to the 0 power is always 1, so that's just going to give us a population equals 42, and that's for this question right here. Okay? And then find the population after 5 years. So population after 5 years, we're going to simply plug in 5 for the time, the n here. So population is going to equal 42 times 1.06 to the 5th power. Okay, so we pop up our calculator here. And we can do 42 times 1.06 to the 5th power. And that gives us that we should be at about 56. Population should be about 56 tamarin for after 5 years. And then now it says draw a graph of the population over time. So we have a couple points already. We know the original population is 42, so time in years. So we'll do 0, 1, 2, 3, 4, 5, 6, 8, 9, 10. We know we're going to go from 40 at 5, we're up to 56. So let's maybe just make this up to, say, 100, 80, 60, 40, 20, and 0 for our population. Okay? So we know, again, at time 0, we started at 42 tamarin. At year 5, we're now at 56. So there's 56 is going to be a little bit above that. Right? Now we're going to want to come up with some more points in here. Now I'm going to show you something on these scientific calculators that can make your life really easy on this, and it's the table. So what you want to do is push table, and it's going to ask you for, it's going to give you some kind of little formula thing up here, y equals. So what we're going to do is push clear, whatever is in there, and we're going to put in this formula just like it looks without the p equals. So we're going to do this 42, and then we got parentheses 1.06, close it, and then what we're going to want to do is we're going to want to leave that as a variable. So we take that to the nth power. Here's our variable down here. It's the third button up on the bottom, from the bottom on the left. Okay, so we put that in there, and then x shows up. We know we want it to be n, but that's just a variable. Okay, so here's a great part. We do that, and we push enter, and then it's going to say, hey, where do you want to start? We want to start when time is 0. We don't want to start when time is negative, because that doesn't really make any sense. And then step means how many points are going to go up by each time. So if we have step 1, that means it'll go up by 1 year every time. So you can do this. You don't have to do it this way, but this just makes a nice, easy chart for us to do. So look, there's 0 and 42. 1, we're at 44.5. So let's graph some more of these. So 1 is at 44.5. I'm going to call that about right there. 2 is at 47. So just under there. Okay, and then now you can scroll down and you can get some more. Look, there's our 5 is at 56. 3 is at 50. 4 is at 53. 3 is at 50. 4 is at 53. So it looks like it's linear, but it really should be going up. It's actually, because we're multiplying by a number each time, so that makes this a curved line here. 75 is what we're going to end up at 10. So there's 70, and there's about 75. So it kind of looks straight, but you can kind of tell it's starting to curve up. Okay, over time. Okay, so that's what that graph should look like. Okay, we're going to take a look at one more example here, but before we do that, let's take a quick comedy break. Oops. Wait, we missed the end of that. All right. One last example. Similar idea here. Cup of fermented yak butter. Tea is left out on a table. The tea cools down as given by the formula, blah, 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 where T is temperature in degrees and M is time in minutes. Is this growth or decay? Since this number here is less than 1, that means that it's decay. what is the growth or decay rate? So we take the 0.72, move the decimal over twice to get 72%. Regardless, always subtract 100%. And that leaves us with 28% negative. So what is the growth or decay rate? So it's decaying at 28%. Okay, or you can just write negative 28 without the decay. Okay, find t when m for minutes equals 0, 1, 2, 3, 4, and 5. So if we're going to do that, our best bet is to put that back in this table function. So go back to table, push clear, and we're going to enter in our function. Okay, so once you get in, you're putting this in here. A lot of people always ask, like, hey, how do I get this out of the power? You got to push the right arrow, and then it'll get it back out of the power. And then do plus 70. And then we push enter. Oops, start. We want to start at 0. And we're going to go up by 1 each time. That's fine. We push OK. And so then it gives us this here to give us a bunch of points. So we've got time and temperature. Something looks fishy here because, oh no, that's right. It starts at 170 degrees and it cools down. Okay. So we know our temperature, we got to go up to at least 170. So we need to make ourselves a scale here. So let's make this, say, 200, 180, 160. Is this going to work? It's only going to go, if we do that, it's only going to go down to 100. So we got to drop by 40 each time, let's say. So that's going to be 160, 120, 80, 40, 0. And then this is time in minutes. 1, 2, oops, let's start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so at 0, we're at 170. Right, so that's going to be about right here. At 1, we're at 142. 120, 142, so about right there. 2, we're at 121. Okay, now you can arrow down. It only asks us to go up to 5, so we can just do that. 107 is 3. That's 100. That's 10, so there's about 107-ish. 4 is at 97, so just under 100. And then 5 is at 89. So there's 90, so about right there. So it looks like it's coming down here, and it's curving, and it's going to eventually kind of flatten out over here. Okay, so we found T when all those points happen. Draw the graph of the temperature over time, which we just did. How long until the T reaches 65 degrees? So you could just go through here and you could scroll down and see when's it going to hit 65. And if you'll notice, it starts to get really close to 70, but never actually gets to 70, does it? Okay, so it just sits at 70, and you'll notice the reason why that is because we add 70 degrees. Okay, to this temperature, and this temperature is never going. This here is never going to get into the negatives, so we'll never get below 70. So how long till the T reaches 65? Never. It'll never get below this 70 degrees, and we'll talk about what that 70 degrees means later on in another section here. Okay. All right, that's all we have for exponential functions. If you have any further questions, please feel free to ask. Thanks.